Welcome to the deep dive. Today, we're tackling something I find fascinating: getting humanoid robots to move like us. Specifically, that incredible agility and balance we have, even in tricky spots.
Right. It's something humans often take for granted.
Totally. Think about something like the swallow balance pose, that one-legged T-shape.
Elegant, but difficult.
Exactly. For us, it feels almost automatic. We've got these complex and sore motor loops, our inner ear, proprioception. It all just works.
But getting a robot to do that, that's the real mountain to climb.
And that's what brings us to this paper, right? Zhang et al. 2025 Hub Learning Extreme Humanoid Balance.
Precisely. This isn't just about basic walking. We're looking at a framework, HuB, for humanoid balance, designed to let robots pull off these really extreme balancing acts.
Okay. So the goal here is to figure out how Hub actually manages this, how it gets around the problems that have made this so hard for so long.
Yeah, and the paper really highlights three main hurdles.
Let's break those down. What's the first one?
Well, first, you've got instability that comes from just using human motion data to train the robot. That reference data.
Yeah.
It's often imperfect.
Imperfect how?
Errors creep in, maybe from video capture, or when you try to map human movement onto a robot body that's, well, different, leads to problems.
Okay, so imperfect starting data. What's number two?
That links to the second challenge. The learning difficulties, because humans and humanoids are physically different. That morphological mismatch.
Different shapes, different weight distributions, all that.
Exactly. What works for a human body might not directly work for a robot's.
Makes sense. And the third? I bet I know this one.
Go on.
Simulation versus reality. The sim-to-real gap.
You got it. That classic problem. What works perfectly in a clean simulation often breaks down in the noisy, unpredictable real world.
Right, so Hub is supposed to have answers for all three of these.
That's the claim. It's got specific strategies for refining the motion data, for teaching the robot to balance despite its different body, and for making sure the learned skills actually work outside the simulator.
And they show this working on a real robot, doing some pretty wild stuff.
Oh yeah, we'll get to that. Things like Bruce Lee's kick pose, the Niza pose, really visually impressive feats on the Unitree G1 robot.
Okay, I'm hooked. Let's dive into that first problem. Getting good reference motion. The usual starting point is just recording humans, right? Video or maybe those motion capture suits with the markers.
That's the standard way, yeah.
Yeah.
You capture a human doing the movement, and then you try to retarget it, essentially translate it, onto the humanoid model.
But you said that data can be flawed.
It often is. Video capture isn't perfectly precise. Marker-based systems are better, but maybe less accessible if you're using existing video data. And even then, of the retargeting step itself.
That's where mapping it to the robot body causes issues.
Right, because the robot structure is different, the translation isn't perfect. A really common artifact is foot sliding.
Foot sliding, explain that.
Okay, imagine a human balancing perfectly still on one leg. That supporting foot isn't moving at all, right?
Right. Plant it.
But errors in the capture or retargeting process might introduce tiny, almost imperceptible movements or drifts in that foot's position in the reference data.
And if the robot tries to mimic that tiny slide while balancing...
It's a recipe for instability. It throws off the whole balance calculation.
Okay, so that's a concrete problem. How does Hub start cleaning up this reference data?
They have a few clever techniques.
Yeah.
First up is something called SMPL initialized retargeting.
SMPL.
Yeah, SMPL is a sophisticated 3D model of the human body. So instead of starting the retargeting process from some default robot pose...
Like a T-pose or something.
Exactly. Instead of that, Hub uses the pose from the human SMPL model as a much better starting guess for the robot's joint angles.
So it's like giving the robot a head start, a more informed initial configuration that's already closer to the humans.
Precisely. It reduces ambiguity, makes the whole retargeting optimization faster and more accurate. They show this in the paper, figure 3, I think, with reduced retargeting loss. It just works better from the get-go.
Okay, that makes a lot of sense. Use a better model to get a better starting point. What else do they do for refinement?
Next is grounded foot correction. This directly tackles that foot sliding issue we talked about.
How?
The core idea is simple. When a human, or a robot mimicking one, is supposed to be balanced on one leg, that supporting foot should be stationary. Period.
Right. Physically necessary.
So Hub identifies these single-leg stance phases in the motion data. If it detects any sliding artifact in the supporting foot from the retargeting step, it corrects it.
How does it correct it? Does it just freeze the foot?
Sort of. It keeps the robot's joint angles the same, maintaining the pose, but subtly adjusts the robot's overall position in space to ensure that supporting foot stays perfectly planted. It enforces that physical realism.
That's smart. Fix the position without messing up the pose itself. Are there other ways the motion data can be unrealistic? Maybe the overall movement?
Yes, absolutely. Think about the center of mass.
Okay. Your weight distribution.
Exactly. Sometimes, due to capture errors or just the different physics of the robot, the retargeted motion might result in the robot's center of mass shifting in a way that's, well, physically impossible for stable balance.
Like leaning way too far over the supporting foot.
Precisely. So HuB uses center of mass filtering. It calculates where the robot's center of mass would be based on the reference motion and its own body model. If that COM projects too far away from the center of the supporting foot, they use a threshold. I think it's 0.2 meters.
Yeah.
It just discards that motion sequence.
So it's a sanity check. If the motion looks physically impossible from a balance perspective, just throw it out before even trying to train with it.
Right. Clean the data by removing the physically implausible stuff.
Okay, and there was one more refinement technique. Transition stabilization.
Yes. This addresses the entry and exit into these extreme poses. These moments are critical.
Because if you're unstable going into the pose,
You're likely going to fail the pose itself. So what HuB does is it artificially extends the stable two-footed stance phase in the reference data that happens right before and right after the main balance maneuver.
it gives the robot more time on 2 feet.
Exactly. More time to settle, find a stable base before attempting the tricky single leg part. And similarly, more time to stabilize after coming out of it, like giving it a longer runway and landing strip.
Makes sense. Provide a buffer for stability. Okay, so we've got much cleaner, more stable, physically plausible reference motions now. But we still have that fundamental problem. The robot isn't human. Its body is different.
Right, the morphological mismatch. And this leads us to the second big piece of HuB, balance-aware policy learning.
Okay, so how does the learning account for the robot's body?
The key insight here is that trying to perfectly mimic the human reference motion, even a cleaned-up one, might still be unstable for the robot because its center of mass, joint limits, and dynamics are just different.
So perfect imitation isn't the goal.
Not quite. HuB uses what they call relaxed reference tracking. During the reinforcement learning process, they don't force the robot to match the reference pose exactly.
They give it some wiggle room.
Exactly. The reward function has a larger tolerance for deviation from the reference pose. They mention a value, sigma equals 0.6 meters, which basically sets how much deviation is allowed.
So the robot can explore slightly different ways of achieving the pose, ways that might be more stable for its specific body.
Precisely. It's less about pure imitation and more about achieving the goal of the pose stably, leveraging the learning process to find what works best for the robot's morphology.
That's clever. Let the robot figure out its own best strategy within limits. But how do you make sure it learns a good, stable strategy and not just some weird, technically balanced, but ultimately useless pose?
That's where the balance-shaping rewards come in. These are extra reward signals designed to guide the learning towards desirable, physically sound balancing behaviors.
Okay, what kind of rewards?
First, there's a crucial center of mass reward, or COM reward. This encourages the robot to keep its projected center of mass squarely within its support base, basically, over its feet.
Fundamental physics of balance right there. Keep your weight over your feet.
Absolutely. Then there's a foot contact mismatch penalty.
What's that penalizing?
It penalizes the robot if its feet make contact with the ground in a way that doesn't match the reference motion. So if the goal is a single leg stand and the robot's other foot touches down, even briefly for stability,
It gets penalized, so it learns to actually do the single leg balance, not cheat by touching down.
exactly, it has to learn the intended balancing strategy.
Right. Any others?
One more. A close feet penalty. This discourages the robot from bringing its feet too close together when standing.
Because a wider stance is generally more stable.
Right. It encourages maintaining a reasonable base of support. So these three rewards, come over support, correct foot contact, and not too narrow stance, work together to shape the policy towards robust intended balance.
Okay, so now we have a robot learning a policy that's adapted to its own body, guided by these shaping rewards, all happening in simulation. But now we hit that third hurdle.
The sim-to-real gap.
Yeah, taking it out of the computer and into the real messy world with noisy sensors and unpredictable physics. How does HuB prepare for that?
This is the sim-to-real robustness training part,
Okay.
and it's critical. They use several techniques. The first is quite interesting, localized reference tracking training.
Localized, what does that mean?
It means they deliberately don't give the robot access to global positioning information during training or deployment. Things like visual inertial odometry, VIO, which estimates the robot's position in the world.
Why avoid that? Isn't knowing where you are useful?
It can be, but VIO systems in the real world can be noisy and prone to drift. Relying on potentially inaccurate global data can actually hurt balance control. Some prior work used VIO in training, but then dropped it for deployment, creating a mismatch.
So what does HuB do instead?
It trains the policy to track the reference targets relative to the robot's own local frame, based on what it senses directly around itself, like its orientation from the IMU and joint positions. This makes the system consistent between sim and real, and less sensitive to real-world VIO noise. It learns to balance based on its immediate sensory reality.
Okay, train it based on local info only, avoiding potentially flaky global data. That makes sense for robustness. What about sensor noise itself, like from the IMU?
They tackle that directly with IMU-centric observation perturbation.
Sounds fancy. Does it just mean adding noise in the simulation?
Yes, but in a specific way. They focus the noise injection on the simulated IMU's orientation readings because the IMU is critical for balance. And importantly, they don't just add simple random noise.
What kind of noise do they add?
They use something called Ornstein-Uhlenbeck noise. The key thing about this type of noise is that it's temporally correlated, meaning its value at one moment depends a bit on its previous values.
So it mimics how real sensor noise often fluctuates and drifts over time rather than just being random spikes.
Exactly. It's a more realistic model of real-world IMU noise. And because the robot uses that IMU orientation to interpret other sensory data, like gravity direction, target locations relative to itself, perturbing the IMU realistically makes the entire perception pipeline, and thus the learned policy, much more robust to the kind of noise it will actually encounter.
Very clever. Model the noise realistically where it matters most. Is there anything else for sim to real?
One more technique. High-frequency push disturbance.
Switching the robot around in simulation.
Sort of, but think smaller and faster than the big pushes sometimes used to train recovery. During training, they apply small, rapid velocity changes, little nudges and jitters to the robot's main body, happening frequently, like every second.
Why high-frequency, small pushes?
The idea is to mimic the constant subtle vibrations and unmodeled physical effects you get in the real world, the small instabilities that can gradually throw off delicate balance. By training the policy to constantly counteract these small, rapid disturbances in sim,
It becomes much more inherently stable and resilient to that kind of real-world jitter during actual deployment.
precisely. It's less about recovering from a big shove and more about maintaining stability amidst constant small perturbations.
Wow, okay. So refined data, balance-aware learning, and this multi-pronged approach to sim-to-real robustness,
Yeah.
it sounds like a really comprehensive framework. The crucial question, though, did it actually work? What were the results on the real robot?
This is where it gets exciting. They tested HuB extensively on the Unitree G1 robot that's a pretty capable humanoid, 29 degrees of freedom.
And the tasks, those extreme balance poses.
Yep, swallow balance, Bruce Lee's kick, knees up pose, plus others like high knees, single leg stand, deep squat. A real gauntlet of balance challenges.
So how did it do?
In simulation, perfect score, 100% success rate across all tasks, which is good, but sim is sim.
Right. The real test is, well, the real test.
And in the real world, the performance was remarkable. They reported high success rates on the physical robot. Crucially, they compared it against other state-of-the-art methods, like H2O and Omni H2O.
And HuB outperformed them.
Significantly. The paper mentions the baseline methods often failed, typically due to those foot contact mismatches or just losing balance altogether, whereas HuB consistently succeeded much more often. Table 2 in the paper really lays out that real-world advantage.
That's a big deal. Going from frequent failures to high success rates on these kinds of tasks is a major step. Did they do any tests to figure out which parts of HuB were most important, like ablation studies?
They did, yes. Those are always key.
Yeah.
They systematically tested the framework with different components removed or changed.
What did they find?
Basically, that every major piece we discussed contributes meaningfully. Removing the relaxed tracking or making it too strict hurt performance. Taking out any of the balance shaping rewards, the calm reward, the foot contact penalty, the close feet penalty, made it less stable or less likely to achieve the intended pose.
And the sim-to-real stuff?
Same story. Removing the localized tracking, or the realistic IMU noise, or the high-frequency pushes each of those changes led to a drop in performance, especially in the real world. It really showed that all these components work together synergistically.
So it's the whole package deal that delivers the results. It's not just one magic bullet.
Exactly. It's a carefully designed system where each part addresses a specific challenge.
Did they test its robustness in other ways? Like, what if something bumps into it?
They did. There's a great visual in Figure 4. They actually kicked a soccer ball pretty forcefully at the robot while it was balancing.
Kicked a soccer ball at it. Seriously.
Yep. And the robot, using the HuB policy, reacted quickly, took a small corrective step or adjustment, and regained its balance almost immediately. It was pretty impressive resilience.
Wow. That's a practical demonstration of stability.
And another test they showed was having the robot perform 10 consecutive Bruce Lee's kicks without falling or needing a reset.
10 in a row.
10 in a row, which really speaks to the reliability and repeatability of the learned policy. It wasn't just a lucky one-off success.
That really underscores the robustness they've achieved.
Okay, so HuB seems incredibly effective for these balance tasks, but no research is perfect. What limitations did the authors point out?
They were upfront about a couple of things. First, some of the specific techniques, particularly the shaping rewards and maybe the grounded foot correction, are quite tailored to balance tasks. They might not directly apply or be the best approach for other kinds of dynamic movements, like, say, jumping or running or parkour.
So it's specialized for balance, not necessarily a universal controller for all motion.
Right. It excels at its target domain. Second, while the policies work very well for the specific motions they were trained on, they don't currently generalize very well to completely new unseen balancing motions without specific retraining.
The generalization problem. Always a challenge in robotics and AI. So it learns the skills well, but can't easily adapt them on the fly to totally different balance tasks. That seems to be the case currently. Creating policies that are both highly proficient and broadly generalizable is still a major research frontier. Maybe future work could build on HuB's principles for balance and integrate them with learning for other movements.
Okay, so noted limitations, but still, what HuB does achieve seems really significant. Getting a humanoid to perform these complex, almost artistic balance poses with this level of robustness, it feels like a real step forward.
I agree. It's a unified framework that tackles those core problems. Reference motion flaws, the human-robot body difference, and the sim-to-real gap in a very integrated and effective way. The level of stability they demonstrated, especially with things like the soccer ball kick, is genuinely surprising and impressive.
It really makes you think, doesn't it? If robots can master balance this well, this fundamental aspect of movement, what does that unlock? What kinds of real-world things could humanoids start doing if they can confidently hold these kinds of poses, stay stable in dynamic situations?
It opens up possibilities, for sure. Think about cluttered human environments, uneven terrain, places where maintaining balance is non-trivial even for us.
And looking ahead, what are the next big mountains to climb after mastering balance like this? Is it about combining this with other skills or achieving that broader generalization?
Probably both. Integrating sophisticated balance with dynamic locomotion like walking, running, jumping is key. And yes, that generalization aspect, creating robots that can adapt and learn continuously in the real world.
Could the way HuB tackled balance, like the relaxed tracking or the sim-to-real techniques, offer clues or inspiration for cracking those other hard problems in humanoid control?
It's certainly possible. The principles of allowing some deviation for stability, focusing on local sensing, and realistically modeling real-world noise, these might be broadly applicable concepts.
It definitely feels like a foundational capability they've significantly advanced here.
Absolutely. Achieving this kind of extreme balance reliably is huge. As frameworks like HuB continue to improve, the potential for humanoids to work alongside us, assist us in complex tasks in our own environments, well, it gets a lot more tangible.
There's still a long road ahead for truly versatile humanoids, no doubt.
A long road, yes. But HuB feels like a very significant and genuinely exciting milestone on that journey.